Hello YouTube, welcome to Antenna tutorial series. Today's tutorial focuses on wideband antennas and it continues with the discussion of log periodic antennas. Now before we study wideband antennas, we need to understand the need for designing wideband antennas and the limitations of narrowband or a single frequency operational antennas. Now going back to the times of half wavelength dipole, which used to work on the frequency of interest lambda by 2. If we talk about dipole, it used to work on the frequency associated with the wavelength lambda, and if we deviated the frequency to any other wavelength than lambda, it would cease to work, or it would drastically degrade the performance of the antenna. Now that was happening because the key point to working of dipoles was the length of the antenna, because those antennas used to work based on the length of the wire used in the dipole. Now if we change the key point or the principle behind the working of the antennas from length to angles, that would make the functioning of an antenna independent of frequency. So I'd like to highlight the point that if we change the basis of operation of antenna from length to angle, then we should be able to achieve frequency independence. Or in other words, we can say that angles do not depend on distance, and hence they would not depend upon the wavelength, and they would help us in making antennas which will be frequency independent, or will be wide band, so as to say. Now the study of wideband antennas starts with the discussion of bow-tie antennas. Now if I draw an illustrative comparison between the lambda by 2 dipole and a bow-tie antenna, we shall be able to understand that the feed point in case of lambda by 2 antenna is distributing its current in a single length of wire in a to and fro motion that leads to dependence of radiation of energy on the length. But when we have an increasing angle of metallic components like this, the structure of a bow tie antenna would be something like this. It'll start with a very small width of metal closer to the feed, and it'll progressively increase in its width. And if you keep on increasing the width till infinity, it will result in in an antenna which will be theoretically infinite in bandwidth. But even if we restrict the length of this antenna to some extent, then we would be able to increase the operational bandwidth of the antenna, which we could have achieved with the similar length in case of a single wire antenna. Now, this discussion leads to the concluding remark that if we associate the distribution of the current in an antenna to metallic elements which are progressively increasing in their width, thereby creating an angle between the two polarities, they will make the antenna a broadband antenna or independent of the frequency. Now, this concept of bow tie antenna was extrapolated to log periodic antennas. Log periodic antennas, they might look similar to Yagi-Uda antennas, but they have a lot in difference as far as the construction and working is concerned. Now we'll talk about the idea behind log periodic antenna. What we tried to achieve was to be able to send many frequencies through one antenna. Now that could be achieved by putting up antenna elements of different lengths in a single boom stick and feeding them with a singular source that would radiate different frequencies. I'm going to draw the diagram for log periodic antenna. Now, in a log periodic antenna, what happens is we focus on increasing the size of the antenna elements as we progress from right to left. For example, we'll start with the smallest antenna element on the extreme right, and then we are going to determine, or we are going to take a constant k which shall be greater than 1. For example, if we take a constant k is equivalent to 1.25, we are going to increase the distance of the next element by 25%. And so what we're going to do is we are going to place an antenna second antenna element, which will be 25% bigger in size than the first antenna, and let this distance be S. Now the third antenna would be placed at a distance which will be 25% more than the distance between the first two elements. So this will be placed even farther off. So this will be S1, where S1 will be S plus 25% of S. And similarly, the fourth element will be placed, its size will of course increase 25% from the previous element, and the distance will also increase, and S2 will be S1 plus 25% of S1. And finally, the last element that we would want to place would have a distance S3, although this distance is not looking bigger than S2, but this certainly is bigger by an amount of 25%. So S3 will be S2 plus 25% of S2. Now same goes with the length. If this is of length L and this one is L1, this is L2, L3 and L4, then L1 is L plus 25% of L, L2 is L1 plus 25% of L1, L3 is L2 plus 25% of L2, and so on. Now you shall be able to figure out the first difference between the log periodic antenna array and Yagi-Uda. In Yagi-Uda antenna array, the main element was placed in the second position, and there was a reflector placed behind, and the directors were placed ahead of the main element, and the distance between the directors was uniform, and the distance between the dipole and the reflector was different from that of director distance. But here the distances are progressively increasing as we go from one element to the other. So that's the first difference. It does not have a uniform distance between the element, and that is the reason this antenna array is popularly known as a log periodic array, because the ratio of L upon L1 and L1 upon L2, L2 upon L3 and L3 upon L4, it remains a constant K, which we decide in the beginning of designing the log periodic antenna. Now going on to the feed of the log periodic antenna. The feed of the log periodic antenna is a crisscross balanced feed. For example, it'll be something like this. So in other words, all the elements in the log periodic antenna array are going to be active element. Yagi-Uda had only one active element, and rest of them were passive or parasitic elements. They were only manipulating the radiation pattern of the antenna. This log periodic antenna will not only work as an array, but it will help us send the signal of frequency ranging from the highest to the lowest. And this particular antenna can be thought of as an individual dipole, which will be responsible for sending a frequency associated with this length of dipole. And similarly, this will be responsible for sending another frequency which will be smaller than the frequency of this element. So in this way, we shall be able to send a wideband signal through a log periodic antenna. As I mentioned in the beginning, that the principle of operation for wideband antennas, they shift from the length of the antenna to the angle associated with the antenna. So here in this case also, a log periodic antenna would be governed by an angle, let us say alpha, which is the angle of log periodic antenna array, and this angle would be determined by the value of k that we select. Now, taking a value of k to be significantly larger, as an example, if we take k to be greater than 1.5, that would mean that going from one antenna to the other, we are going to increase the size of the elements by 50%, would result in creating some active elements and some passive elements, because the center frequency of the log periodic antenna would allow only a few of these to work correctly. For example, if we take k to be greater than 1.5, only the elements with the center frequency and a few elements on both the sides will be able to radiate, and the rest of them would not actively radiate the signal. However, they will perform the functions of reflector and director. They will be acting as parasitic elements. But if we want to make sure to use each of these elements as as active elements, then we must keep the value of k to be limited to let us say values closer to 1.1 to 1.25. So that goes to show that going from one antenna to the other, we are increasing only 10% to 25% in terms of length. So that was the idea behind creating wideband antennas using a mathematical sequence in terms of its geometry. I'm sorry. So there is this vague logic of increasing the size and the spacing between the elements based upon a constant ratio, which is predetermined to design an antenna to create an angular effect that will not only increase the directivity but also help in making the antenna frequency independent. And if we make the number of elements to be infinite, then this could theoretically achieve an infinite bandwidth of operation, but that is not possible. So I guess the basics of designing a log periodic antenna and the basic functioning behind wideband antennas and bowtie antennas is clear. And if you found this tutorial helpful, then please consider subscribing to my channel, and you could share the video to someone who really wants to understand these topics. And thank you so much for watching this video and other videos in the series, and you have a good day and a good life. Bye.